In the spring of 1951, the San Juan Islands off the northwest coast of the United States became the scene of the laying of the world's longest single-length submarine high-voltage cable. The project was designed and carried out by the Bonneville Power Administration. Have you heard of the Pig War of 1870? Well, it was on the San Juan Islands, the last part of the United States territory on which the British flag was flown, where this war was waged. At that time, the treaty establishing the boundary between Canada and the United States was not definite, and a dispute arose as to the ownership of the San Juan Island group. An American settler shot a pig owned by a British settler. Both countries immediately moved troops on the island of San Juan. For 13 years, this joint occupation continued until the boundary was finally settled in 1872 by Kaiser Wilhelm I of Germany. An old British fort still stands today as a memorial of the war in which no shot was fired except the shot that killed the pig. The people of the beautiful and economically important San Juan Islands were promised power a long time ago. To serve these islands, it was necessary to find a way to transmit power from the great federal projects on the Columbia River over hundreds of miles of high-voltage lines. Several alternate plans of service were investigated, including a submarine cable from the mainland to Orcas Island on the north. Then overhead lines spanning the narrow reaches of water from island to island, using high precipitous banks to obtain sufficient clearance for the long spans required. The plan finally selected included a 4.5-mile submarine crossing of Rosario Strait, a wood pole line on Decatur Island, and another 2-mile submarine cable to Lopez Island. The core of the entire plan was the submarine cable. To select the proper cable, Bonneville engineers investigated several different types of design. Final specifications called for a submarine cable covered for mechanical protection by galvanized steel armor wires laid in a jute bedding around the 3 rubber-insulated copper conductors. Each conductor was wrapped with a Monel metal shielding tape and a little over 1/2-inch wall of rubber insulation. The cable was manufactured in one continuous 7.5-mile length, weighing nearly 750,000 pounds. The first step in manufacturing the cable was to strand the 61 individual lead-coated copper wires into phase conductors. Next, these were insulated by folding rubber compound strips around each conductor and compressing them by forming wheels. After 8 separate layers were built up, a temporary lead sheath was put over the outside to serve as a mold. The cable was then placed in a large vulcanizing tank in which it was cured under pressure and heat for several hours. After the curing process had been completed, the temporary lead sheath was peeled off like a banana skin. The conductor was then immersed in water for 12 hours and tested with 170,000 volts DC for 15 minutes and 49,000 volts AC for 5 minutes to ensure that the insulation had been properly applied and cured. 3 of these individual Monel-type conductors were then twisted together with jute fillers to make a firm, rounded core. This assembly was wrapped with a heavy tape binder and placed on reels in 2,300-foot lengths. Factory splices were required to join the 2,300-foot cable length. The 61 copper wires in each conductor were separated and silver soldered. When the birdcage of wires had been individually soldered, the strands were compressed back into a smooth, firm assembly very little larger than the original conductors. The individual conductors were then re-insulated with rubber tape. An electric heating strip was wound around the joint and an asbestos blanket wrapped over it to vulcanize the rubber tape. These splices were tested with the same AC and DC voltages as the original insulation. The core was covered with a cushion of jute, then wound in one continuous operation with 400 miles of 1/4-inch galvanized steel armor wire. From the armoring machine, the completed cable was fed directly over a capstan 40 feet above the ground into the gondola cars, where it was coiled about a wooden core in the center. The cable was carried from one car to the next by means of vertical loops, and the cars were sealed with lumber. As a safety precaution, the gondola cars were linked with two heavy chains and a bar welded through the coupling pin to prevent accidental opening of the coupling in the freight yards or during transit. After a final test, the shipment was appropriately launched by breaking a bottle of Atlantic Ocean water on the end car and started on its 3,000-mile trip to the West Coast. In the meantime, Bonneville engineers were completing plans for installation of the cable. Studies of weather records for the spring period of the previous 6 years were made to determine probability of favorable weather. This record had to be matched with tidal information, since the velocity of the water in the channel would be one of the major factors during the cable laying operation. To assist the Bonneville Power Administration in this problem, a special study was prepared by the Coast and Geodetic Survey, predicting the actual velocity of the water in Rosario Strait for each hour of the day from April 1st to June 1st, 1951. From this prediction and the weather studies, the dates of April 16th to 18th were selected. On these dates, the tidal currents would be near zero for several hours in the late morning and early afternoon. The main hazard in cable laying is paying out the cable faster than the ship moves. Unless this is prevented, it may result in permitting kinks in the cable as it piles up on the bottom of the sea, as well as the possibility of running out of cable before reaching the opposite terminal. To control the rate of payout of the cable, an underwater profile was made from fathometer readings taken by the Coast and Geodetic Survey. At each station on this profile, the proper tension was calculated and the angle at which the cable would enter the water. To control the movement of the cable ship and obtain an accurate record of its position at all times, survey parties were to be established on shore at each end of the course and at locations off to the side. 4 such points were selected for the Rosario crossing. Radio telephone communication was provided from each survey party directly to the top deck of the cable ship. Readings determining the position of the cable ship were to be taken every 2 minutes. In the meantime, the cable train was completing its transcontinental trip. The manufacturers publicized the huge shipment by signs placed on the sides of the cars. These signs read, Okanite Submarine Power Cable. For 25,000-volt electric transmission. World's largest high-voltage cable. Diameter, 4 2/3 inches. Weight, 19 pounds per foot. Total weight, nearly 3/4 million pounds. One continuous cable over 7 miles long. For Bonneville Power Administration. The Puget Sound Power and Light Company has installed a number of cables across the deep waters of Puget Sound using a specially equipped cable ship. Bonneville Power Administration was able to charter this ship, named Puget Power, for the cable laying operation. To test the ship's equipment, check the communication facilities, and assure complete coordination, all shore and ship crews were assembled for a trial run in Seattle's Lake Washington. There, an actual operation of laying and picking up a mile-long piece of used cable was performed. Meanwhile, the 9 gondola cars were being spotted on the dock in Seattle for reloading to the cable ship. The cable loops between cars had been protected by burlap wrapping, which was pretty well worn by the time it reached Seattle. Before removing the cable from the cars, both ends were opened up and connected for a high voltage test to ensure that no damage had occurred during transit. $46,000 volts DC were applied to each of the 3 conductors for a 15-minute period. final test indicated clearly that the cable itself was not injured in transit. By this time, the cable ship had been brought around to the pier from Lake Washington and was spotted at the dock for loading operations. A shiv 8 feet in diameter was suspended over the gondola cars at approximately the same height as the capstan at the factory. This was necessary to allow the armor wires on the outside of the cable to lay back into place as it had been during the original manufacturing process. In the cars, this armor wire tended to basket and open up. The end of the cable was threaded through this shiv over the stern of the cable ship. Upon entering the ship, the cable was wrapped 4 times around a 92-inch diameter drum. The purpose of this drum was to pull the cable from the cars onto the ship. Later, during the laying operation, this drum would be utilized for providing braking power to hold the cable back in deep waters. Immediately forward of this large drum are 3 small shivs which drive faster than the drum and thus keep the cable tight to prevent slippage. 2 cable wells were available for storage, one forward and one amidships. It was necessary, with the 7.5-mile length of cable, to store portions in each of the 2 wells. Over each of these wells is located a large shiv driven by steam to pull the cable to the top deck. At all points of sharp angle on the cable, the diameter of the shivs is quite large to avoid damage due to bending. In the wells, a large crew of men was necessary to manhandle the cable snugly into 34-foot diameter coils. 5.25 miles of cable were stored in the forward well, which required 17 layers of better than 1,500 feet per layer. Normally, an excess length of cable is ordered for submarine jobs. With 2 separate crossings, it appeared advisable to keep the cable in one continuous length, so that the remaining cable from the shorter crossing would be available for the second, more difficult crossing. This also would allow any leftover cable to be in one piece. A slot was cut in the top deck between the 2 holes. A loop of the cable was lowered through the slot, and the coiling process was repeated in the second cable well, where the remaining 2.25 miles of cable were stored. In this manner, the cable remained in a single continuous length. As each car was unloaded, the railroad switch engine spotted the next one under the large shiv, and the operation was continued without interruption. The complete loading operation was performed in 2 normal working days. The tag end of the cable was opened up, the conductor sealed with rubber tape to keep out the seawater. Then, the armor wires were formed into a pulling eye for use at the start of the laying operations. Since it would be necessary to know the actual tension on the cable during the laying, a special shiv calibrated against a strong spring was provided at the stern of the boat. The cable was threaded under this shiv to the fantail. As the tension varied, the shiv was raised and lowered against the spring and indicated the tension being applied. Overnight, the cable ship was towed 65 miles from Seattle to Lopez Sound. Meanwhile, ship and shore crews were assembling at Anacortes and completing final preparations for the laying. Early in the morning of April 16th, survey, radio, and work crews were loaded on small vessels and transported to their stations. The cable ship itself was anchored offshore from the Lopez terminal. Cable laying operation was about to begin. Although this operation would require less than 3 hours, the preparatory work up to this moment took more than a year of planning and preparation. A helicopter was used to carry a small, light rope from shore to ship. This rope was attached to a steel pulling line, which was then drawn to the ship and fastened to the pulling eye of the submarine cable. A tractor on shore pulled the submarine cable from the ship into the terminal. In this operation, it was necessary to use power from the steam winches to feed the cable off the ship. During this time, the cable ship remained at anchor. School children and local residents came down en masse to ensure an ample number of sidewalk superintendents. Handling and laying of this cable was a rugged he-man job, and there was little time for relaxation or the more pleasant diversions, except, well, yes, there were a few girls present. The communities in the area took the event as an important civic affair. They selected a cable-laying queen and her princesses. In breaking the bottle over the cable as it reached shore, the queen cut her finger slightly. This was the only accident during the entire cable-laying operation. When launching formalities were completed, the end of the cable was secured to a buried anchor on the shore, and the ship was ready to proceed across Lopez Sound. Since the ship has no means of self-propulsion, navigation was provided by 3 tugs, 2 secured alongside near the stern and 1 forward. The navigation officer on the top deck of the cable ship communicated by radio to control the coordinated operation of these 3 tugs. Over the loudspeakers, throughout the ship, and over the radio, an announcer gave the time every 2 minutes. The transit men on shore and the observers on the ship took simultaneous readings at each of these 2-minute intervals. The shore crews transmitted their transit readings to the plotting table on the top deck, where the information was laid off on a master control map, and the actual course of the cable ship was thus recorded. The position of the ship with respect to the course was made available to the navigating officer. A second crew on board ship in the meantime was recording the angle of the cable entering the water, the number of revolutions of the main drum, which gave us the actual length of cable paid out to that point, the speed of the revolutions of the main drum, the actual tension of the cable, and the calculated tension desired at each location. It was impractical to bring the large cable ship into the shallow water near shore. So as it approached the Decatur Island terminal, the cable ship was brought to a stop in deep water. There, a scow was placed in position near the stern so that sufficient length of cable could be laid out to reach the shore terminal. With the measured amount of cable on the scow, workmen then bound the armor wire to prevent unraveling and sawed the cable in 2. Shore crews would be coming the next day to drag the cable up to the terminals from the scow and backfill the ditches. The cable ship was towed around Decatur Island to Anacortes, where it lay overnight. Early in the morning, she was moved to anchorage off the Fidalgo terminal in preparation for the second day's laying across Rosario Strait. Procedure at Fidalgo terminal was similar to that of the preceding day. Submarine cable was pulled ashore by tractor, anchored, and the ship began moving across the strait. crossing of this strait, 4.5 miles in length and in much deeper water, was more difficult due to the greater tensions required, a stronger wind, and eddy currents at the center of the channel. Because of these adverse factors, it was necessary to operate the ship at a higher speed, better than 3 miles an hour at times. Deviation from the straight line course was as much as 400 feet, although the total amount of cable used in excess of calculated requirements was only 500 feet. After completing the crossing, the cable ship was again anchored, the shore length paid off onto a scow, and the cable pulled ashore to the terminal. At all shore terminal structures, the cable end was split, and each of its conductors was brought out to a separate insulated terminal. On the islands, the terminals were mounted on wood pole structures. At the Fidalgo Island substation, the cable was terminated on a steel frame. The protective armor wire was anchored in a cast iron casing known as a spreader head. The 3 individual conductors were carried through this spreader head up to the pot heads. Shielding tape on the outside of the conductors was protected in this portion by neoprene rubber and fabric tapes. To relieve the electric stresses between the conductor and the ground shielding tape, a tapered stress cone was built up on the end of each conductor. This stress cone was then inserted through the base of the terminal and a porcelain bushing placed over the upper end. This pothead, as it is called, was later filled with a compound material to keep out moisture and air. A gasketed cap nut was attached to the top of the pothead and provided a terminal for attachment of the overhead lines. The cable was energized on July 22, 1951. This event was celebrated by the population of the San Juan Islands at a large community gathering with members of Congress, civic leaders, and the Bonneville Power Administration participating. The cable has been in successful operation since that time, and so a promise has been fulfilled. A promise made more than 13 years ago that someday in the future, power from the mighty dams on the Columbia River would be brought to the San Juan Islands to light homes and provide energy for the growing industries of the island.